This can be one of the more intimidating lessons in chemistry, the equilibrium ice problem. Usually in equilibrium, you're used to them giving you a bunch of information about a bunch of different things at equilibrium. They ask you some question, you plug them in, you set that equal to KQ, you solve for whatever the missing variable is. But that's not always how it happens. There's another class of problems where they get a little bit more complicated, and so I'm going to teach you how to do those today. But before we can do that, how do you know that you have to do this? How do you know that you have an ice problem? Well, read the problem carefully as always, and what we're going to do is we're going to ask ourselves, does it mention that the amounts, the partial pressures, the concentrations, are they at equilibrium? If they're not at equilibrium, for instance, if they tell you what the initial conditions are, or how things start, or you put this blah 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 in, then you probably have an ice problem. Ice problems often give you an initial condition and ask you to figure out what's happening later when the system comes to equilibrium. So here's our example. I won't read it out loud. If you guys want to pause, you can read that entire problem. But there's a reaction, gives you a K value. We're going to pull it out, and you notice that what they tell you is the initial concentrations. Actually, they don't even tell you concentrations. They give you moles and liters. So don't forget that first thing you got to do with any of these problems is make sure that you have an acceptable K expression unit, either partial pressure or molarity. Here we have moles and liters, so we're going to convert these into molarities. So the initial concentration of the nitrogen is something we can calculate, as well as the oxygen. So we have a box, some reaction vessel. We put nitrogen and oxygen into the box. Notice it doesn't mention NO. The initial concentrations are, well, for nitrogen we got 5 moles divided by 5 liters. So that's 1.0 molar, and same for oxygen. Same numbers there. So those are our initial. And our K expression here we can write NO squared over into O2 molarities. But that K value is only true at equilibrium. Notice the amounts they give you are not at equilibrium. They're initial amounts. They're the amounts that we put in before they react. So we cannot use those numbers. We cannot plug those numbers into the K expression. So what do? Well, we're going to make an ice chart. Once we make one, you'll see why we call them that. So what we're going to do is we're going to start by asking ourselves, what do we know about the initial conditions? And we're going to make a little row below there. So the nitrogen, we know we have 1 molar before anything happens. And for the oxygen, we have the same. And for the nitrogen monoxide, we don't know anything. Actually, we do know something. It's not mentioned that we put any into the reaction vessel, so we should assume that there isn't any. So we're going to start with none of that. At equilibrium, clearly that can't be the case because our K value isn't 0, so we know that this is going to react. So we make our little chart. What we're going to do is we're going to make 3 rows and a column for each of the reactants and each of the products. Plus we'll have a 4th column over on the left to give our labels, and the first label is the initial. That's our initial row right there. And then we're going to ask ourselves, how does this reaction change as it gets to equilibrium? That'll be our last row. So we have an initial row. What are the concentrations at the beginning? Second row is how do they change, and the third row is what are they at equilibrium, which gives us our name, ice. This is an ice chart, initial change in equilibrium. So now we want to start filling it out. So we'll start with the change row. I'm going to put in a negative X for the change in nitrogen, and the reason is this. We don't know how much nitrogen is going to react, but we do know that when it reacts, it's going to be used up. So that's where we get our negative sign, because it's a reactant going to be used, and an X because we don't know how much. And then we move forward to the oxygen, and we're going to see that the same thing is true of the oxygen, and also that it's going to be related to the nitrogen in this. There's a 1-to-1 ratio there. So it's also going to be negative X. So what's different about the product side is 2 things. One, we're going to make it. rather than use it. So it's going to be positive. But you'll notice that it has a coefficient of 2, so we're not going to make x, we're going to make 2x for every x that we use. So we're going to put plus 2x there. Now the equilibrium row is pretty easy. All we're going to do now is add the initial row to the change row. So for nitrogen, initial is 1, change is minus x, so 1 minus x is your equilibrium value. Same for oxygen. And then for NO, 0 plus 2x is 2x. So there we go. Now we have all of our equilibrium values, and we have a K expression, so we can go ahead and plug those numbers in to that expression and solve. So let's go ahead and do that. So here's our K expression, and we can start plugging in the numbers we know. The first number we know the K value is 0.1. So we can go ahead and plug that in. We know the NO value at equilibrium is going to be 2x. We're going to plug that 2x in, keep the squared. Then the nitrogen, we're going to substitute 1 minus x there. And for the oxygen, we're going to substitute 1 minus x there. And now you see that we have an equation with one unknown that's solvable. But it's a quadratic. In fact, often these ice problems do involve quadratics. So what are we going to do? Well, we could give up. We can do the use x is small approximation that I've described in a different lesson. I'll just go ahead and tell you right now that this one, the K value is too large, and so that x is small approximation won't work here. So we're actually going to have to solve this. And there are many tools on the web for solving these, but this time, just this once, we're going to solve it by hand, using a little trick I like to call maths. So let's go ahead and just start rewriting this in different ways. That top 2x quantity squared turns into 4x squared. We're going to FOIL the bottom. We get 1 minus 2x minus x squared. And I'm going to go kind of fast here, so I don't want this whole video to be just watching me do algebra. So we will go ahead and, if you want to pause and figure out what I did at any step, feel free to do that. But I'm going to multiply the bottoms out. That gives us an expression that looks like this. Then we're going to distribute. Now we got that. Now we're going to subtract 4x squared from both sides to give us a something equals 0. And now we're going to rewrite it into ax squared plus bx plus c form. And that's what we get. So we get an a of negative 3.9, a b of negative 0.2, and a c of 0.1. So now we pull out the quadratic formula, shown here with the exponent of 1/2, because I couldn't figure out how to draw the radical on this text editor. So we start plugging in our values for a, b, and c, and it looks like that, and we get this big mess. So we just start simplifying. You can get out your calculator and verify these if you like, and it was all simplify and simplify and simplify and simplify. And so now we're finally to our plus or minus. So we've got our plus or minus values, and simplify those a little bit. And we're left with these two numbers, which simplify to our two solutions of negative 0.187 and positive 0.136. So the answer is one, but not both of those two things. And so we have to figure out which is the correct answer. So let's do that. So going back, these are our answers. But remember that x means something. X means something. So if we go back and substitute these x's in, what we'll find is that one of these answers will not make any sense at all. And that's the one that doesn't make sense. And why not? Well, because if you look, 0.187 negative times 2 is how much NO concentration we have at the end. So according to the first solution, the negative solution, we would have a negative molarity for NO. We would start with none, and then we would use some up, which is nonsense. It's impossible to use something up if you have none of it. So that one cannot be the answer. So only the 0.136 can be the answer. And so we assume that that must be the right answer. It's very tempting at this point then to pat yourself on the back and move on and say, well, x is 0.136, but notice that 0.136 isn't the answer to any of the questions they asked us. Answer the question. Well, what was the question? The question was, calculate the concentration of each component. So we need three answers. We need to know what the NO is at equilibrium, what the O2, and what the N2 is. But we already have expressions for those in terms of x, and we know what x is, so we just plug x in now, and we have our answers. We plug 0.136 into each of those. So the N2 is 1 minus that, which is 0.864. O2 is the same, and NO is 0.272. So those are our answers. And you can even check to make sure your answers are right, because we know when you plug these into this expression, we should get 0.1. So we can do that. Go ahead and plug the numbers back in. NO into O2, plug those in, get an answer, and we get 0.0991, which rounds to 0.1. So 0.1 was the answer we expected there, and that's what we got, so we're pretty confident that we did that right. That's your first ICE problem.